So here's another example where we're going to do a propagation of air calculation. Let's assume that we're doing what we call gravimetric determination. In this case, we've got chloride in a sample, and we want to collect all of that, and we're going to do that by using a selective reagent. Silver ions in solution will precipitate and bring silver chloride down. So all the chloride then gets gathered in this solid that falls out, and that's fairly pure stuff. And we know that this works because the KSP is very small. Recall that the KSP is actually the equilibrium constant for the solid dissolving. So we have the ions divided by the reactants, and the activity of silver chloride, any solid activity, is by definition 1. So these two are going to be very small since their product has to be very small. So this analysis involves taking a sample, usually a solid sample, and dissolving it up. So we have an unknown amount of chloride in solution. It's brought down in a complete manner to bring everything into a pure silver chloride mass. We collect that mass, dry it out, and weigh it. Then we can calculate the moles of this material by using the formula weight. The number of moles of the product is a 1-to-1 relationship with the chloride, so all of the moles of chloride are known at that point. Multiply by the formula weight, or the atomic weight of chloride, we get the mass that's just due to chloride. We compare that to the original mass of the unknown sample, the solid, and we can get the weight percent. So this involves weigh the sample, and we'll do this by weighing by difference. Dissolve it in water. So we add a small amount of deionized water and stir till everything dissolves. Add the silver nitrate reagent. And the white precipitate is our silver chloride. We digest the precipitate. In this context, digesting means to stir and heat the sample so the silver chloride clumps together. This makes the particles easier to gather in a filter. Now we want to make sure all the chloride has been precipitated down, so we add a few drops of silver nitrate to see if any cloudiness appears. If so, we have to continue the digestion. We need to add more silver in this case. We collect the precipitate. We're going to gather the precipitate in this special filter. It's actually a crucible that has a glass mat at the bottom of it to trap the fine particles and enable us to get all the silver chloride product. Before we begin collecting, we do a very thorough job of cleaning out the filter so that nothing changes during the experiment. So we clean, dry, and weigh the filter in the empty form. Next, we pour all the supernatant through the crucible while it's on a vacuum system. We'll use a very dilute nitric acid solution to help coax the solid into the crucible so that we get every last speck. We dry it. First, we turn off the vacuum and break the vacuum seal by hand. Then a set of tongs helps us transfer the crucible to a clean beaker. A watch glass will help us keep dust out of the beaker. Then the sample goes into the oven at 110 degrees for an hour. After drying and cooling, we weigh the silver chloride. So we're going to need a mass of silver chloride that was gathered in a crucible. Let's suppose that crucible plus silver chloride weighs 25.6158 grams. And let's subtract from that the mass of the empty crucible. So the difference gives us the mass of the silver chloride that we found, that we gathered in this experiment. Likewise, when we measured out the sample, we started with a full weighing bottle, and let's imagine that had a mass of 21.9372 grams, and we're weighing by difference. So out of this, we take some sample and weigh the bottle again, and we have 21.3531 grams for the final. So the difference is the amount actually used, 0.5841 grams of sample used. Now to calculate percent silver chloride in the original sample, we take the mass of the silver chloride and divide by the formula weight silver chloride, and of course that gives us moles of silver chloride. So if we multiply this by the ratio of 1 mole of chloride per mole of silver chloride, we convert this moles of chloride. If we multiply that by the atomic weight of chloride, that should give us grams of chloride. So if we divide that by the grams of sample, this should be the fraction of the sample that is chloride by weight. So multiplying by 100 reports that as a weight percent. Let's call that term R. So let's plug into this and get real numbers. So the mass of the silver chloride is 0.2437 grams divided by 143.3209 grams per mole, and we multiply by the ratio for the moles of the stoichiometry is just a ratio giving us 1. And so the atomic weight of chloride we find in the literature is 35.4527, and divide by the mass of the sample, 0.5841 grams of the sample, and times 100 gives us an R value 10.32, and the next digit is 0% chloride. To calculate the error, since this is multiplication and division, we might expect the relative errors to accumulate. So the relative variance should be the relative variance in each of these terms in our multiplication and division. So there's going to be a relative different variance for the silver chloride mass. If we divide that by the mass of the silver chloride, take the square of that, we get the relative variance there, and that should be a reasonable number. Now we could also do this for the formula weight. Even though this term is going to be extremely small, let's do that. I find that the formula weight has an absolute error of 9.2 times 10 to the minus 4 grams per mole, according to the literature. So we divide that by 143.3209, and that quantity squared. Now that's going to be a very small term, and we'll see that it's very small. Likewise, the atomic weight has an uncertainty of 9.0 times 10 to the minus 4 grams per mole, divided by 35.4527 grams per mole. That quantity squared will be quite small. And add that again to the relative variance in the sample mass. And that will be divided by the mass of the sample, that quantity squared. What is the relative error in these weighed materials? Well, the variance in the weighing step should be the same in each case. Each of these masses were the result of two weighing steps. Let's imagine our balance has a reproducibility of 1 in the 4th decimal place, so that there are two weighing processes, so there's two errors. Each of these variances, they would add to a similar term, so we'd have two of those. So the overall variance for our weighing is 2 times 10 to the minus 8. So the standard deviation for a weighing is equal to the square root of that. That is also going to be equal to the uncertainty in the silver chloride mass and the uncertainty in the sample mass. So if we put that in to our equation, the relative error is equal to 1.4 times 10 to the minus 4 over a mass of 0.2437 quantity squared plus 9.2 times 10 to the minus 4, 1433209, that quantity squared, plus 9.0 times 10 to the minus 4 over 35.4527 quantity squared, plus, again, the error for two weighings, 1.4 times 10 to the minus 4, divided by the mass for the sample, 0.5841, that quantity squared. I get, for this first term, 3.30 times 10 to the minus 7. The next term is much smaller, 4.12 times 10 to the minus 11. So this is really negligible compared to the first. Just as we might have guessed, the next term is 6.44 times 10 to the minus 10. Once again, pretty much negligible. And the final term, 5.74 times 10 to the minus 8. If we take the square root of this sum, we can go right to the relative error. And I get for that 6.2 times 10 to the minus 4 grams. So to get the absolute uncertainty, that would be our ratio that we just calculated times the actual value of R. Well, that would be 6.2 times 10 to the minus 4 times the value of R, 10.320%. So this product, a value of 6.39 times 10 to the minus 3%. In other words, our value of R is 10.320 plus or minus 6.39 times 10 to the minus 3%. Oddly enough, the first uncertain digit is this 0, and we actually have an extra decimal place in our final answer.